Good evening, everybody, and very warm welcome to this course. So, I am Manoj Nandi from ICAR Kolkata. So, I am going to mainly solve the assignment questions, and obviously, if you guys have any question at any point, please feel free to stop me and ask, and I will definitely try to clarify those. So, let's uh, start today's session. Let me now turn off the camera actually. Okay, so good evening again, and today is our first session. So this course is based on this metallocene and metal carbene based organometallic compounds, and which are some of them are very much industrially important. And as you have probably gone through the lectures of Professor Sujit Kumar Patra. So as he was telling that it is plastic. So this is the mainly you can understand the how important this process and these polymers are. So we will start with some questions of previous year assignment questions actually. So let's start with this particular question. And meanwhile, I will while I am solving these questions, I will obviously discuss about the some of the backgrounds of this particular concepts, and we would continue our discussion like that. So the first question is who has given the this particular modern concept of polymerization or polymer. So these are the available option, and the so this is basically a historic background question, and you need to know about this. So Professor Hermann Staudinger, he is actually considered to be the first man to describe this particular concept regarding this polymerization chemistry. So in his times like 1920s, like in this time period, what it is that then chemists thought that this kind of large molecules are not with this kind of covalent bond. They thought that some kind of aggregates of small molecules are formed, and that's why the properties of monomer to uh, polymer that change, and that's because of generally aggregation. So that's the then belief by other chemists. So then actually the Schrodinger. So you may know him by the Schrodinger reaction also. And he is the same man, when same scientist. He also proposed this thing. So he proposed that the chain of paper clips is a good model of polymer like polylactic acid, which is shown here. So he proposed that not just um aggregates of some van der Waals force that only act. So here during formation of polymer, what happens? Covalent bond is actually forming. That's why the chain length is increased, and the mainly the major thing is the property of monomer is changing, and and the reason behind is that covalent bonds, not other interactions. So that Hermann Staudinger is the first scientist to propose this particular model to explain this polymer. Then this particular field actually erupts, and many more uh, discoveries have been done. And so the starting point is this his discovery, and he actually proposed this particular and this particular polymer chain is obviously composed of some small monomer units like that. So you are seeing that all are same monomer unit, and they are the repeating units, so that's why this particular polymer form. So he is the first. So that's why the option would be uh, is Staudinger. And all the other names, so they are also very much famous. So Jacob Berzelius, so he is also very much famous. So he is probably from many back, means 1800th century. So then he actually proposed about chemical name and chemical properties, chemical symboling. So he's kind of pioneer of chemistry also. But polymer chemistry is quite new, and Berzelius is not the modern concept he didn't propose. And Sarikawa, so he is also one of the Nobel laureates in this particular polymer chemistry. So he actually uh, discovers or propose the find out that some of the polymers are actually semiconductors. So semiconducting polymers. So that's his field, and he actually discovered this kind of phenomena and received Nobel Prize. So Sarikawa is one of the Nobel laureates in this particular polymer chemistry field. And Ziegler-Natta, so very much well known to all of us, all of chemists and polymer scientists, so all of them. So this is particularly one Ziegler-Natta catalyst. We are very much well known, and 1947, 50 around that time they got the Nobel Prize, and for synthesis of that polypropylene PPs and this particular catalyst actually. So for that they got a Ziegler-Natta. Ziegler-Natta got this particular Nobel Prize. So they all are the Nobel laureates actually. So let's little bit talk about that Ziegler-Natta catalyst, what I am talking about. And so this particular gentleman is uh, Giulio Natta, and he is called Ziegler. So both of them got Nobel Prize for this discovery of this particular Ziegler-Natta catalyst. So what they observed is, so previously what is done is very much well-known polymerization technique is radical-based polymerization, right? So they are actually very much chances are high of forming different branching products. Like this kind of branching uh, products can be formed, and not much controlled way we can do polymerization. So what they found that when they use this particular TiCl4 and triethyl aluminum, this particular reagent, or sometimes this particular chloro reagent also they use, and they have observed. So here is their observation actually for polymerization. So they actually selectively, or you can say control way, they can get only this uh, linear polymerization, and this can be achieved due to the properties of these particular metals, which we will discuss a bit now. And so this is their observation. So what they have observed, that when this propene is reacted with this titanium chloride and this aluminum, this particular two metals, they observe this formation of this isotactic polypropene PP. So tacticity I will come later. So just now only concentrate about that linear thing is forming. So only consider that now. Tacticity I will come just a bit later. And so this is their first observation, and it is one of the other observations. So there they have observed that again this linear polymer can be formed, but they are actually this symbiotic polypropylene. So here you can see all are not in same way or above. So above, below, this kind of fashion they are stitching together and making this particular polymer. So this is their observation. And so in 1 atm pressure in 20 to 70 degrees Celsius, they got this linear polymers. So that's the uh, one of the great discoveries in this particular field. And molecular weight they have achieved up to 10,000 to 20,000. So, that's the initial foundation of this signal catalyst. And so it is what we are talking about, that when we are doing polymerization using traditional methods, means using the radical polymerization. So branching is one of the issue, and obviously quenching of radical is very much easier. So low molecular weight oils are only can be achieved at that era. So that's why this particular discovery is very much important at that particular time, so that they can achieve linear as well as this molecular weight up to this much high, 10,000 to 20,000. So that's the uh, importance of this particular discovery. Well, so now, how the reaction happens? So that this titanium at first reacts with this kind of aluminium's ethyl unit, ethyl unit, because here is this kind of thing is possible. So it is negatively charged and with aluminum. So here we have a vacancy in titanium. So after this thing, this kind of this is it. Now question is how it is forming. So we know that in titanium, we have that in the outer cell we have DXY, where it is vacant DXY is present in titanium. And I am talking about this particular case. And dx square minus y square, this particular thing is field. So that's the outer cell we are talking about of this particular titanium species. And how it is reacting with olefin. So for olefin, we all know that pi bond it is. So we have pi and pi star. Uh, So now it is your HOMO actually, and it is LUMO. So LUMO is vacant and HOMO have two electrons. Sorry, it is not pi star, it is pi, right? Pi and pi star. So this is having two electrons, and this is your LUMO, which is vacant. Now this at first this olefin, this particular electron can be donated to vacant. Uh, let's say vacant DXY of titanium, and it is filled. So when this particular electron donation happens, what happens? And this is the reason of this kind of reactivity also. So dx square minus y square, which is filled, they can also back donate the electron in its pi star bond, anti-bonding or pi star, we can say. So that's how this kind of titanium and olefin reacts with each other, and the you can say dual activation kind of thing. So electron is donating and giving, and that's how this titanium and this particular pi bond is interacting with each other. And now after that, when this particular thing happens, this kind of transition state you can expect as one electron is donating to its anti-bonding. So that's why that pi bond is now cleaving, and it is having some majorly single bond character, because we know that bond order is lessened when pi star having electron. So that's the general thing how this thing happens. So that's why this double bond is now is partially single bond double bond character is there. So bond order is now lessened. It is not two now. This after this kind of aggregate or transition state, we can say this formation of this titanium CH2 bond happens like this, and this one of the ethylene ET unit is transferred to this position. So this kind of olefin insertion happens, and this ethylene is transferred to, it's migrated to this particular CH position, and you can end up with this kind of species, which is two. So that's how the formation of alkene metal complex is happening, and that is well explained by this particular orbital interaction. So here we are seeing that this kind of orbital overlap is uh, also very much feasible due to this kind of approach, because it is also kind of step matching is there, and nodes are also matching. So that's the reason why this particular orbital interaction is happening. Now we are in this particular state, which is two, which is this particular state. Now, for polymerization, we know we need multiple units of monomer to react. So now the second unit of your alkene can react in same fashion, because it is nothing but this particular unit. So there we have this particular ethyl unit. Now we have this prolonged CH2 CH methyl and ethyl unit. So this is the prolonged part, and titanium's reactivity remains same, because this particular vacancy is again created due to this ethyl shift. Now again, this can react with your olefin unit in the same way, because it have now vacant DXY and filled this particular DX square minus Y square. So in the same way, in the same this kind of fashion, the second unit of your olefin can react, and you can in and this ethyl in the same way will be doing in the shift, and again you can end up with this particular unit, and this particular shift is very much selective here also. That's why you are only forming that linear polymer, right? Because of steric reason, and also you can say electronic reason, both are are playing over the here a particular role to do this particular this kind of interaction, not the other way. Because if the other thing happens, let's say if this kind of aggregate forms, so you will see the reason why it is not forming, because here it is chloro, and not only chloro, many other bulky ligand are present sometimes. So there, this kind of interaction is very much prominent. So this kind of static reason is one of the issue, that it only reacts with this the center where bulkiness is less, and that's why only linear chain you are forming, not branched one. So that's one of the reason of this particular reactivity. Now, this particular thing can repeat after much cycle, until the chain termination happens, and you can form your linear polymer up to that limit, 10,000, up to that point you can form. So after propagation, this chain propagation happens. So now we need to do that termination approach. So there are several approaches how the termination happens for this kind of Zignal-Natta polymeric reaction. And so one of the uh, uh, process is beta elimination from the polymeric chain. So this is your polymeric chain, and this kind of beta hydrogen can be. So this is your this particular this CH, this particular CH is there, this particular CH. So this is your beta, right? Alpha beta. This is beta hydride. With sorry, beta hydride elimination, uh, this kind of thing can happen, and you can end up with this kind of polymer, which are having this N group, which is alkene. That's how that one of the way to do this termination step. And this is titanium hydride, which is evolved during this particular termination step. So this is one of the way. There are another ways also. So this is the second way. So here beta elimination with hydrogen transfer to monomer. So this is another way. So now here you can see this particular hydrogen at first what is happening? It is directly transferring or reacting with your titan. Sorry. Uh, your titanium unit and titanium hydrogen is forming. Now what we are seeing that this hydrogen is not directly reacting with titanium. So other part which are having that olefin. So let's say this is your another last equivalent of your olefin that or monomer for your polymer. So now titanium is reacting like this, and this particular hydrogen is shifted or reacted through the CH2, the terminal position of your olefin, so that you are end up with this CH2 CH3. So CH2 CH2 CH3. This particular unit you are end up with, and meanwhile this particular elimination is happening, which is leading to this particular titanium unit isopropyl group is attached with titanium, and you are ending up with hydrogenated product of this particular thing. So if you do hydrogenation over here, you are just having this particular polymer. So here this hydride is not transferring to titanium, it is transferring to carbon. So that is it's doing kind of reduction. So that's here they are telling that beta elimination with hydrogen transfer to a last monomer. So that's how this is one of the other way of termination. And this is kind of same hydrogenation. So here what is happening is this is titanium, and what I am saying here actually. So if you do the hydrogenation over here, right? So hydrogenation is done like palladium charcoal, so that hydrogen is absorbed in palladium charcoal surface, and it can do the reduction. And another thing when we use this Raney nickel, so there also hydrogenation is reported. So hydrogen is absorbed in this particular surface, and they perform this particular reduction. So that's what they are saying here also. So here you are seeing that with this particular titanium species, the one of the hydrogen can come and do the final reduction to break the last chain or the termination step actually. So this is one of the other approach for this termination of polymerization reaction. So we have seen that for Ziegler-Natta. So at first titanium is reacting with your aluminum unit, and with this kind of olefinic double bond it's reacting by dxy and phi, and there the phi and the phi antibonding or pi star with dx minus pi square. And after that the chain propagation can happen because monomer unit can keep coming, and due to this selectivity all of them should be linear. And lastly, for termination step, these things I have just explained with beta hydride elimination with titanium hydride like this, and another thing is directly uh, gone to last unit of your monomer unit, and lastly this thing. That's how termination can happen, and you can end up with your uh, polymer. So now coming to your Ziegler-Natta, right? That reduced selectivity, what I am telling about. So, yeah, it is seen that primary insertion occurs in stem to give this only this particular regioselective product, or in the metal alloy is insert in the terminal position. So that's why actually that linear chain is only forming, and that's due to what previous slide I have just explained. due to steric effects and electronic effects. This is uh, happening, and that's uh, uh, very much well understood. It because here you can so electronics is also there because you can think of this kind of hyperconjugation, and always this is having some of the this particular thing. Uh, this kind of polarization is there because it is stabilized via your this particular thing. So when we react it with titanium, so metals are positively charged. So this kind of electronics is also favored, that sigma minus and sigma plus, so relatively positive center and relatively negative center, they react with each other, not the reverse. So that's is one of the other reason for this particular selectivity. And obviously, steric reason is obviously there, because if titanium is there, it can face interaction with your CH3 or ethyl, methyl, any alkyl group which is present in this particular position. So that's the one of the thing. Now let's see that what we are discussing over here, that isotactic and thin diatactic. So why this particular two different thing is happening? Just changing a little bit of titanium to vanadium, or some bulkiness with increase of bulkiness, how this particular change is happening. It is going isotactic from thin diatactic. So how it is happening? That can be explained by via this. Now, so this is the transition state what we are seeing over here. So here it is written like it is. So, but now in three-dimensional, when we need to consider the stereochemistry, we need to see this kind of this or this kind of uh, conformation. So that we can understand that stereochemistry, how and why it is happening. So when we are forming that particular transition state, there are two possibilities, right? So where metal is titanium. So two possibilities are there. So this is so this methyl is coming from your that particular sheaf, which is attached to your titanium, and this is from your olefin. So now consider these two carbon units. So here, what we can see that here that CH3 is in above phase, and here with carbon, this CH3 is your below the phase, right? This come from your olefinic unit, let's say your monomer, right? And this particular thing came from, so when we are reacting these two, we are getting like this kind of intermediate, right? So methyl. So after that particular shift of methyl, there previous case I have shown with ethyl, now it is methyl. In the same case, you can consider ethyl also. So with that, so this is the this part. Now here we are seeing that they are in the trans fashion for A, and here you can see with both methyl are in his first fashion. So now, if you want to choose between these which is more stable, definitely trans one will be much more stable, because it can have a lower steric interaction with this two methyl. And here we have a severe interaction between these two methyl groups. So due to steric effect, obviously always A going to favor over B. So when A is favored, we are end up with this kind of chemistry, right? Uh, this kind of thing where for this kind of cases and uh, you are ending up with this kind of trans stereochemistry. Why it's trans? Because here one of the methyl is Indo and one of the methyl is Indo. So that's how it can be controlled. And in another fashion, so if the cis thing happens, then only we can achieve this kind of chemistry. So what it is, the how this particular thing is happening. So they have told that when we met with metal, this kind of some kind of bulky group is attached, then what happens if, let's say, this particular case. So if Y is very much bulky, some steric interaction would be there with this methyl and Y. So for that, it prefers to go to this kind of C space, where this particular methyl-methyl interaction is lesser compared to your this methyl and Y, this particular interaction. So when this particular Y or the ligand with your metal is very much bulkier, then only this kind of thin fashion we have observed or they have observed, and then only they have got this particular product which is isotonic. So that's the reason of forming of this particular two different things. So that's the issue. And here the main reason is that basically kinetics is there, right? Because here you are seeing that it is done in very much low temperature with this kind of group, so that it prefers to form this particular stable transition state with this kind of anti-stereochemistry. So that's why it's slower and this particular thing happens like this. And here it is doing in room temperature or sometimes heating condition. So that's the thing of TCP speaking and that's how you can control the formation of this two kind of toxicity. So that's how you can control this thing. So, okay. So, this is the for the first question. I have discussed briefly about this kind of signal data catalyst. So later on, it would come again and electricity also. And so another question was asked to some of you in the forum actually. So I thought of clarify that particular doubt also. So there, it is said that with particular NMR, we can calculate this number average molecular weight of the polymer. So some of them are want to know how we can calculate that. So I want to just discuss how we can easily control with NMR and this particular number average molecular weight of your polymers. So, from this particular thing, we can actually calculate degree of polymerization and also the number average molecule. So, before that, degree of polymerization is number of obviously the number of monomeric unit in a macromolecule or polymer that is present. Means number of N that is present. So that is your degree of polymerization. And how it is calculated? It is calculated by this particular formula. You can divide your number average molecular weight with M0. So it is molecular weight of your repeating unit or monomeric unit. So by dividing these two, you can calculate your degrees of polymerization, right? So this thing is your number average molecular weight, and M0 is molecular weight of the monomeric. And this is the formula for number average of your molecular weight. So that's the basics. Now coming to your NMR thing. So how we can correlate these two things, uh, and we can easily calculate it. So degree of polymerization. So how we can calculate that? So this is the general formula for that, or just you can just derive that also, but for just you can just follow this one. So at first we need to take the integral of your repeating unit. So what are the integrals? So this is the integrals of NMR. So when we have taken this particular thing as C, it is coming to 155, almost like that. So these are the integration, so that at first you can put over here, and so here it was around 155. So it is 155, right? Now the number of protons of your repeating unit. So the number of photons of your repeating unit, it is obviously 4, because two hydrogen is there and two hydrogen is there. So these are your repeating units, and this is your terminal unit. Mhm. So repeating, so how much protons? So 4. So here we can put 4, right? So means 155 by now number of protons of your N group. So N group we have just one, it is just methyl, so it would be 3. And integration of the N group, so integration how much we have taken? 3, 2.79, almost 3, 3 by 3. Now you can just, with this easy equation, we can calculate the decrease of polymerization. So uh, again, I am explaining over here. So at first, what we need to do, that we need to identify your uh, this N group. N group proton comes for this particular unit is here. So we are seeing that one singlet is forming in your 3.4 region area, and it is your for N group. Now, if we take this as our reference, and we can integrate it is at C, then we can integrate this particular area, which is your repeating unit, and it would be obviously much higher. And we and using that we can calculate. So if we integrate that, we get around 155. So now just we what we have seen earlier, 155. We have 4 protons, 4, and here it would be 3 by 3. So if we calculate it, we would get around 38.8. So that's how you can easily calculate your degree of polymerization, which is 38.8. Now what we need to do, we need to calculate that number average, right? So we remember now how dp can be calculated is by this. So this is the molecular weight of the repeating unit, right? Now that number average would be repeating unit molecular weight into degrees of freedom. This thing. Now just you can calculate the molecular weight of this particular thing. So here it is uh, two carbons is 4, and O is 24, and oxygen is 16. 20, it is 44. So this is the molecular weight of your repeating units. So N group generally is not taken because only methyl, and it does not contribute much. So that's why only the repeating unit, which is present in your polymer in much higher amount, that is only considered, which is 44. Now just do this thing, so 38.8 into 44. Now, if you do the calculation, uh, 38.8 into 44 would come around 167, I think. So it would come around 1700. So this should be your number average molecular. So that's how you can easily calculate that number average from your NMR data. So I hope you understand this particular thing. If you have question, you can ask now, and then we are going to solve one more this particular thing and move ahead to our other assignment question. So you guys have any doubt, you can ask. Okay, and you can write in the chat box also. In the meantime, if you have any question, I can answer that. So, okay, fine. Now move forward to the another problem. So here also we need to calculate the number average molecular weight. So how we can do that? So obviously we are going to start with uh, sorry, degree of polymerization. So uh, now we can use our formula. So at first the area of your repeating unit integral. So which is here 72, right? Right. So it's so 72 is, so how we get that? Because the end group here we are seeing we are having 4 into 2 means 8. So two terminal or two end groups are there which are similar. In total we have 8 proton. Yes, so that's why the aromatic region, so these are the aromatic proton. So the aromatic region it is taken like this. And this particular thing it is in your CO stars. So with CO it is attached, so it come little bit higher region in fourth, and that's your repeating. Uh, so again, it is for uh, two hydrogens actually. So one and other way it is kind of linked, you can say. So for two hydrogen. So here it is number of protons of your repeating group. Now you can do other things. So 8 integral area and number of protons is also 8. So ultimately you are ending up with here 36. So this is your degree of polymerization. Now M0 we need to calculate. Right. So let's check. So these so dimer of this thing, so means 4 carbons, 1 2 3 4, oxygens are also 4, and we have 5. Means it would be uh, around 100 now 114, and it is 36. So now this particular M0 is 114. Now you can do this multiplication. Let's see. So would be around 4,100. Okay. So that's how you can calculate number average molecular weight with just NMR. So that's one of the techniques how you can do this thing. So I hope you understand. Now we can continue our discussion on this particular other problems actually. So coming to this one, so they want to know which of them are uh, inorganic polymer. So let's see what are those. So the first thing with phosphorus and nitrogen, what is this written over here? It is called actually your this polyphosphagene, right? So this particular the polymers, so which have having this phosphorus and nitrogen, so phosphagenes, and followed by polymer. So that's how that naming came. And here for this particular example, what you are seeing over here, here we have fluoro group, right? That's why it's called polydichlorophosphogene. So this is one of the uh, 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 polymers which is famous in this area, and this can be synthesized from this particular ring opening polymerization. So later on, you can I will explain that also, and obviously you can go through your lecture videos. So they are again it is going to be explained in detail, and in the further class I will, if question comes, obviously I am going to explain that in quite detail also. So here what is happening is just the opening is happening, and uh with what and it is if this one of them opens, so you can see that you'd end up with some uh, linear chain unit, and that can couple with other opening partner, and that's how it can propagate also. So that's how propagation for particular step can happen with heating condition. So with n up to 15,000, this particular technique can be used. And these are the other reactive reagents. So here you are seeing that all of the basic uh, reagents are used. So some kind of methoxides or ethoxides, some kind of primary amines or secondary amines. They are used to break this kind of bonds. So these are the reactive centers. So it can pass, let's say, this particular attack is happening like this, followed by ring opening, and you can end up with removal of one of the fluoros or fluorides. So that's how you can end up with this kind of faults actually. So uh, it's Na plus and it's Cl minus, NaCl. For amines, it's H plus, and here it is Cl minus. So that's how particular thing happens. Uh, so how it so let me so that's how it happens actually. So uh, again, so should not show over here. From here I should have shown. So here you can see particular attack is followed by removal of this tail miner. So that's how it is. It can be happening, and you can make uh, many different polymerization polymers using this kind of various variating these R groups with amines or alcohols. So here you are seeing that's how it can be free. So this is for this phosphagene as a monomeric unit, and it is called that also that polyphosphagene. So this is one of the inorganic polymer, and here it is actually called polydimethyl siloxane. So here you are seeing the particular structure. So a silicon oxygen bond, and this kind of thing is also very much popular in this kind of polymer industry. And you can so in many materials it is used, and this particular thing is called polydimethyl siloxane, and it is also one of the inorganic polymer. And when oxygen is not there, so it is called polysilenes, just polysilenes without oxygen, and again, with silicon bond, this particular bond that polymer propagation happens. So silicon in this kind of way, and branched or linear thing are possible over here, and they are called so with R and heading, and with your use and with rigidity how you want to do that, you can change, and you can transform the your material. So with R, let's say if it is normal alkene, so then it will be very much flexible one. So rubbery kind of thing, very much flexible material you would expect. When it is olefin, some amount of rigidity is there, so it is bit hard polymer, and when it is alkyne, it is much more rigid and very hard material you can synthesize. So with that transforming this particular R group, so not only alkene alkyne, so with fluoros, amine, so if you can do that, you can end up with different materials. So that's for polysilanes. And here also the same thing. If methyl can be transformed to other things, and here the bonding happens with silicon oxygen. So in this way, it actually occurs. And it is also a inorganic polymer. So we are seeing that all of them are inorganic polymer. It should be option, right? And all of them are all of the above. So all of them are your this particular polymer. Now coming to this thing, so there they want to know uh, the practicity is observed. So we need to know what is practicity first. So we are seeing this in the Ziegler. I hope you all remember. Here we are seeing that this kind of plasticity and how it is changing with the this particular stereochemistry of this particular methyl group. So they are actually chiral centers. So with changing this, we are saying that it is isotactic, it is syndiotactic. So how this particular thing is happens, what we have discussed now. For the classification, we want to know, and what is the importance also. So plasticity is the relative stereochemistry of adjacent chiral centers, right? So we are saying that adjacent chiral center, and within a macromolecule or polymer, obviously. The practical significance of plasticity rests on effects of physical property, obviously, because not only for stereochemical assignment only. So when it propagates and it forms that uh, big macromolecular structure. It affects very much of your physical property of your material itself. So with that particular polymer is depending upon this particular this kind of stereochemistry, the properties of the polymer actually varies heavily, and this is very much dependent on this particular arrangement. So that's why this particular thing we read and learn, and we can just uh, uh, able to understand how this thing happens and how it affects your material. So with isotactic polymers, they are composed of this particular isotactic macromolecules in all the are located in the what we are seeing is that all the substrates are located on the same side of your macromolecular backbone. So this is your backbone, and here you are seeing all of them are sitting in the above phase, right? All of the uh, substrates or R group is in the above phase. So they are in the same side of your backbone. So that's why it is called or it's named as so it's kind of impact naming and it is named as isotactic macromolecular polymer. So they obviously consist of 100% meso diad isoselective polymer. So why it is meso? Why it is called? Because you can see these are the diodes. So why diode? Because we have taken only 2 units, so that's why it is diode. When you take let's say 3 centers or three above the phase molecule, so that's why it is called this diodes. And for this particular this kind of polymers, so 100% meso that's isolytic unit is there. And when we or you would made this kind of molecules where all the R groups are in the same phase, you can expect this particular property. So that's why you are we are actually classifying this particular different polymer because and this is the reason we are learning practicity because when this particular property is there, all of the polymers would be in semi-crystalline and often from a helix kind of configuration, right? So that's one of the major property for your isoactive polymer, where all of the substance are in the same side of your backbone. So this is what this particular isotactic polymer. Now coming to your thin diatactic polymer. So now here you just recap. So in the Ziegler-Natta, so this is one of the observation we have seen that they have chosen this particular condition and they able to form this particular polymer where they are anti to each other. So in the adjacent stereo center are in the different phases. So if one of them is above, another should be below. And that's how it is maintained above, below, above, below. So that's how the chain would propagate. And this is called actually your this thin diatactic polymer. Just a minute. Okay, so that's how we have they have formed these syntactic polymers, and now let's look into its properties. So we are here. So this is the thin didactic polymer. So in this thin didactic polymer or syntactic, so both of the naming are popular for this kind of polymers, and this particular macromolecules have alternate position along the chain. So what we are seeing over here, alternate are the in the different phases or different planes, we can say, if one of them is above and another is in the below. So the macromolecule consists of 100% racemo diet. So these are called the racemo diet. So it came from your racemic mixture. So that's how this naming came, because here you can see that if it is R, it is S, and if you see over here, it is S, it is R. So it is nothing but your enantiomer. So when two enantiomer are present in your solution, it's called a racemic mixture. In the same amount, if it is there, it is called racemic mixture. So that's how this particular naming came also, because we are seeing that this particular diodes and they are racemic to each other if we consider this kind of thing. So that's how they are called that 100% racemo diodes. And when this thing is happens, so this thing is came from that what it is called mesodiode. Why? Because in the meso compound we expect to have one sigma plane, so that's why it is called your meso biochemistry, right? Because for let's say what is the fuller example I can give is let's say meso tartaric acid, right? So very much well known, and uh, the meso concept actually. Tartaric acid we all know, and mesotartaric acid. So we have for that this kind of biochemistry. This mesotartaric acid, and let's say one of them is uh, 8 and dithin. This is acid, tartaric acid. This is active. Why it is called mist? Because we have one sigma plane that is passing, and that's why it is not chiral. And same thing we can see over here, because all of them are in the same phase. We can expect this particular sigma planes in all of the phases, and that's why we are calling it as mesodiode. That's how that particular namings are coming, and this is why it is mesodiode and it is racemodiode. So which is your synthetic polystyrene unit of so this is one of the example of synthetic polystyrene and made by metallocene catalysis of polymerization. And what is the characteristics for this kind of alternate stereochemistries polymer? It is called crystalline. So this is actually crystalline with melting point of very much higher. So all of them or major amount of them are this crystalline material you can form if you have kind of arrangement. Now one of the other thing, it is called your adaptive polymer. So here what happens, it is here you can see that the are placed randomly along the chain. So the percentage of mesodiodes, meso means this kind of diodes, is between 1 to 99%, and with the aid of spectroscopy, obviously we can pinpoint that position, and uh, in terms of the triad tension. So if you have this kind of arrangement, with two above, two below, then this kind of thing is there, then it is called atactic. So it's quite these are also there. So one of the characteristics is uh, what to say, one of the categories there, and in detail in lecture you are always able to read that. So now coming to our question. So we know now that what is toxicity and why it is used. So now where the toxicity is observed. So for LDPs, it is low density polystyrene units, and they are this kind of polyethylene units actually. So for polyethylene, we are seeing this kind of thing. So here, after formation of polymer, what we can observe is this kind of. So there are no chiral center are present. So if there is no chiral center, so if the substituents are not different, so above, below, below, so there is no question of that. So that's why for this kind of thing, this LDP, we cannot expect to have this capacity because only because there is no uh, stereo centers over here. But for PVC, we can see it is one, it have one fluoro group. So when this particular 10 forms, so we can obviously going to observe this particular chiral center because it is having fluoro. Now it is C to another unit would be something, it would be above or below, so that will depend upon different things. So that's a different issue. But obviously, we are going to observe this because it is chiral centers, right? This should be one of the options. But for polystyrene, again, we should observe uh, this. Because again, we are getting the what chiral centers. So I think here, although one of the answer is given, but B and C should be the right option. and it is not a, and it is also not possible. So um for only this polyethylene unit, there are no kerosene is there. So that's why that we can call it as there are no toxicity should be also. But yes, it is very much possible. Now these things I have just discussed. So, now moving forward. So, yeah. This one we have uh, uh, just learned in quite detail. So how Ziegler and Nata developed this and how the action mechanism goes and all. And for that itself, they got a Nobel Prize. And the year is uh, 1963. They have won that particular Nobel Prize for this discovery of particular Nata catalyst and synthesis of this uh, propylene, propylene and short termed as PP. And particularly this Nobel Prize is given for developing isotactic PP in this particular polymer. For that, they have given the prestigious Nobel Prize in 19. Now, coming to these, they ask if crystallinity means if crystallinity or hardness or orderness is higher, when crystal is from when your thing is more ordered, so then only crystal can be formed because crystal is nothing but uh, the state of orderness, what we say for crystallization also. State of orderness. If it is ordered, then only crystalline can be formed. And when it is ordered, so we can just think that when things are ordered like this, obviously the things it would be more denser, the solution would be harder because it is ordered, and the material would be hard. So obviously they comes with that with the term crystalline linity. And when you have this kind of unit where no orderness is there, then obviously it would be softer because so its solvation is always easier for them, and they would be much softer for us. So for where order is not there. So now if we consider that, so both density and optical clarity increases. So density obviously going to increase, but optical clarity cannot be increased because if it is ordered like this, so and it is more dense, so penetrating this particular material by photons or light is hard, obviously because it is more dense and it is less porous. But for this kind of substance where it is less ordered, they are actually light can easily go, and this cannot be true actually for you can say this polymer. And mechanical strength increases for crystallinity and Young's modulus decreases. So that's not true because Young modulus we know that the force that is needed to stretch, and when it is ordered we need more strength to stretch or do the this particular delta L movement for this kind of material. So delta L with force, right? We basically going to need more force, and it should be higher for crystallinity when it increases. So that's what here they have written. Modulus increases and density is also increased. that should be the option. And they are not true. And both solubility obviously not going, obviously solubility is decreases, or barrier properties are not going to decrease because they are hard material, they are more denser, young modulus is higher, so they would be barrier property would be good, not decrease. So that uh, how you can uh, eliminate this particular option also. So that's how you can solve this one. Now coming to the other thing, so there they have asked is which of the following properties is not possessed by polyethylene. Oh, sorry. So here, little polystyrene, just a bit. Need to correct that. Just uh, so let's continue. Okay, so the property is not uh, possessed by polyethylene. So again, they are actually information based question. So you need to know about the properties of polyethylene. So I know this will described by in the view itself. So you can just go through it and you can so that's based completely based on this kind of information based thing. So so they are very much easy to prepare, obviously, and chemical resistant they show, and they are tough, but they are high coefficient of friction. So this is not cause or have polyethylene does not have this particular property. Uh, so their friction is low. So again, information based, you can just check it out. And now coming to this, so they want to know which of the polyethylene uh, uh, produced by copolymerization of ethylene and other alpha olefin. So at first come to your HDP, so high density polyethylene polymer. So this particular polymer, so obviously it's monomer is ethylene, and there you are seeing that single chain type of thing is there. So that's why it is highly dense because it is linearly formed. So that's why it would be much more in order and it would be much more denser. So no branching is happened. So like Ziegler-Natta, there we learned how only linear polymer can be formed with this that kind of catalyst. So that they are called actually kind of thing is called high density polyethylenes, and they are thermoplastic and very much having high strength density ratio, and for pipe storage, this kind of plastics are used, and the melting point of is very much high. It should be enough because it's more denser and more ordered. So let's say uh, high density polymer is very much this kind of. So this cannot be formed by ethylene and other olefin, alpha olefins, because R group would lead to kind of branching, and which is not what high density polyethylene is suggesting. So it would be not the option. So the right option is this kind of thing. So low density polystyrene, so linear polymer with significant number of short branches. So here you can see, if you can see this kind of backbone kind of thing. So small branches be there, and like this, and they are low density due to this having this kind of small branches. So two units of this kind of threads, you can say, cannot come much closer, like for this HDPE can, because there are no such branching is there. So that's why they are low dense, means they are having some porosity between them. So that's why they call low density polymeric ethylene, polyethylene. So they are formed by ethylene unit and alpha olefin, this kind of thing. So that's little some kind of little branching to happen, because without that branching cannot be happening. If it reacts like this, so you can see this kind of branching is formed. Branching is there. That's how it is conditioned. LDPE, so uh we uh so the first one what I have discussed is linear low density polyethylene. So that's why it is LLDP, and it is linear, but some amount of this kind of thing is there. But for LDPE, what happens? We can see many more branches like this. So that's why they are low dense polyethylene units, right? And yeah, that's the one of the example of this LDPE, and this cannot be formed in this particular two reagents. So for that, other much more thing is required. So in the coming class, I will obviously discuss about those. And now coming to this UHM uh, WP, ultra high molecular weight polystyrene. So what it is said, it is more ordered HDP. So HDP, here we have seen that high density polymer, and it's not only high density, it is calling as ultra high molecular weight. So this is conventional HDP, this kind of thing. So when this remains in very much longer chain with this kind of units and arrangement, it is called UHMPW or WP, means molecular high molecular weight polystyrene, because the repeating units are higher, so that's how MW would increase, and that's how it is called a particular thing. And for this particular cases, again, we need to have this kind of uh, chain, and and the thing is polyethylene. So no alpha olefin can be used to make this kind of. So if alpha olefin is used, there are some kind of branching would be forming obviously, and you cannot call that as this particular. So that's why the right option for this given is here LLDP, linear low density polyethylene. So if alpha, so if this kind of thing is there, so little bit, but good. Okay. Now coming to this, so there they have they want to know that polypropylene with coke. So this is the monomeric unit. So this is propene, and when it's react, it remains in this kind of fashion. And it is polypropylene, and they want to know that what is the correct statement among these this four options. So uh, so coming to these, so exotactic polypropylene is amorphous in nature, but when we learned about exotactic, what we have seen that is semi-crystalline and not amorphous kind of. And for this, it is also crystalline with high melting point. Now, for polypropylene, it cannot be true. It cannot be amorphous. So, eliminated. That is semi-crystalline in nature. It is not true again because here. So this is the classification. So atactic is they are actually amorphous. So that's the thing. And again, it is eliminated like that. So here you can see that attractive arrangement, right? This kind of thing. So two, one unit is only your homotactic diad, which is present. Where uh, not homotactic, mesotactic or mesotactic, and between this 1 to 99%. Any of this thing happen, little bit disorder. Uh, want to ask something? Let's see. Uh, Here it will be in this PPT, na, PPT will be uploaded for issue. So whole PPT is will be uploaded. So now coming to this diatactic is semi-crystalline. So in the previous we have seen that in a indirect it is in semi-crystalline nature. And here you can see that also syntactic and isotactic, both of them are semi-crystalline. Only difference is that temperature, melting temperature. Here you can see. So it is true and it is amorphous. Obviously not true. So with practicity, we can predict these kind of things, and we have learned that very much well now. Yeah. So that's the questioning. Very much simple thing. Coming to this particular question, so there they ask that correct statement about thermoplastic and thermoset polymer. So you need to know at first what are those things. So when so these are the thermoplastic and thermo setting. So here you can see the main difference between these two is this cross-linked bond. So which is missing for thermoplastic, but for thermosetting we can see many cross-linked bonds are present between this kind of monomers. So strong covalent bonds between polymer chains. So two different polymer chains, but they are cross-linked with a strong covalent bond. Then they are called thermosetting, and they are remain hard when heated. So thermal strength is quite good for this kind of polymer. And for this kind of cases, it's weak intermolecular forces. So just no covalent forces are there, only let's say van der Waals forces, no non-covalent forces actually acts between this kind of polymer chains, and no crossing is. So that's the major difference between thermoplastic and thermosetting or thermoset polymers. So there actually that critical difference came. So the critical difference between thermoplastic and thermoset is how the material behave during your cutting process. So what is that when uh, it's actually that hardening of your plastic. So that's the process actually. So here you can see that unreacted monomers can be present like this, and can be this kind of branch thing. So they are actually heated, or other techniques are also there so that they can be hard. So hardening of material. That's what you can say for this particular current thing. And with zone two, or the next step, they are kind of gel is forming, because here you can see that more and more bonds are forming, and monomeric units which are unreacted or present in your material is now less. And when this happens, kind of rubbery gel, it is forming a giant macromolecule. It is forming like this, and lastly, when this kind of solid bond is forming, and the chain length is very much higher, then the kind of solid or glassy solid is formed. Then this particular phase, the your material is hardened, or your polymer is hardened. So that's the thing of budding. So when that happens, so the chemical bonds uh, uh, in the process. So thermosets or thermosetting polymer strengthen when cured, but from chemical bond. So that strong covalent bond which are formed. So that's their thing, and they are impossible to break actually. And for thermoplastics, they do not form any chemical bond in this particular process, and they can be recyclable. That's the major difference, and the physical difference is the three-dimensional makes them stronger. For thermosets, obviously, these particular bonds are there and more heat resistant than thermoplastic. So that's the thing why this thing happens actually. So as this particular thing is formed, they are hardened, they are more temperature resistant. So that's how the thermosetting thing will work. So that's the basic brief things about thermoplastic and thermosetting. Now let's check. So thermo are become a liquid on heating, obviously, because it is thermoplastic, not thermos setting. So they are not heat resistant. So when it is heated, they can be liquefied. And so this would be your one of the option. And the next option says all the thermoplastic polymers are amorphous in nature. It's not true because all thermoplastics are amorphous in generation like that is not true actually because some in this case rubbery gel is also there so semi-crystalline thing can be forming. It is not true. So polymers may be semi-crystalline obviously and both crystalline and amorphous. So thermoplastic can be any of them. Uh, Maybe semi-crystalline, maybe crystalline, or maybe amorphous also, not only amorphous. So that's why there are soft in nature. So which is not true because of this kind of uh, thing formation, it is hardened when heated. So that's not true either. Formations are very much hard in nature. So that's why would be your right option. Now coming to our today's last question. So one simple mathematical question. So let's say if you have these four samples of polystyrene. Polystyrene, you remember that styrene, styrene, and polystyrene. Uh, like this, right? Polystyrene are prepared with molar masses with 20 kilodalton, 25 kilodalton, 30 and 40. Now, if you want to ask to calculate the number average of molecules. So, number average uh, formula was Ni it early. This was a formula, right? And just initially, right, we have learned that. Yeah, so that's the formula in a like that. So in a number of molecules having we are here. Now you want to know that this particular number average and the samples are very narrow much obviously that we are seeing and now it is for the same number of molecules of each sample within the mixture. So that's how they have simplified our problem. They told that all of the number of the this particular mass are same. Means number of uh, molecules having molecular weight 20 kilodalton equals to number of molecule having 25 equals to 20, sorry, 30, 40. So all of the uh, molecular weight having molecules are numbers. So let's consider it as capital N. N. So uh, in number of uh, molecule having 20. So in number of molecule having 25 kilodalton molecular weight and so on. Now just write that. So N into 20 dot N plus 25 dot N plus 30 mm, N. So plus 30 and 40. 40 and so unit is kilodalton. Yes, and the number of so here 20 diagonal having n, 25 having n, so is also in n. So now in we can write like this. So 30. Let's calculate 20 25 is 115 by 4. And now just do this. It would be exactly 20.75, which is also the given answer. And we are having the in a note like this. So very much easy math, and that's how we can calculate number average. So we have done much more complicated thing like than this. So with the NMR thing, we have done that in real research in how you can calculate that. So that's how you can do that. And for exam purpose, it's kind of easy numerical questions can come and you can solve that easily also. So I hope you understand. So there are no more questions discussed today. So now if you have any question you can ask now, or we can close today's session. If you have any question, any query, you can ask. It seems fine. So thank you again. Thank you for okay. So thank you for joining again. So in the same time we will meet in next coming week. So same time Friday 6 to 8. All right. So again thank you all for joining, and we would continue our discussion in our next class. You in next class. Thank you.